Artemis II marks NASA's return to crewed deep space exploration for the first time since Apollo 17 in 1972. 4 astronauts will launch aboard the Orion spacecraft on top of the Space Launch System rocket, traveling beyond low Earth orbit, looping around the Moon, and returning to Earth after roughly 10 days. This mission does not attempt a lunar landing. Instead, Artemis II is designed to validate every major system required for future missions: launch, deep space navigation, life support, communications, radiation exposure, and high-energy atmospheric re-entry. It represents the transition from experimental testing to operational human spaceflight beyond Earth. For over 50 years, all crewed missions have remained within low Earth orbit. Astronauts aboard the International Space Station experience microgravity, but they are still protected by Earth's magnetosphere, which shields them from much of the cosmic radiation present in interplanetary space. Artemis II will take humans beyond that protective field, exposing Orion and its crew to a radiation environment not directly measured in decades. This exposure is not theoretical. Radiation sensors embedded throughout Orion will collect continuous data on particle flux, shielding performance, and cumulative dose. Astronauts will also wear personal dosimeters. These measurements are essential for planning longer missions, particularly those to Mars, where crews would spend months outside Earth's magnetic protection. Orion itself is a fundamentally different spacecraft than those used in previous decades. Unlike the Space Shuttle or vehicles servicing the International Space Station, Orion is designed for autonomous deep space operations. Artemis II will be the first time humans live and work inside Orion for an extended period. The spacecraft's environmental control system must maintain breathable air, regulate temperature, remove carbon dioxide, and manage humidity in a sealed environment far from Earth. Automated systems performed well during Artemis I, the uncrewed test flight in 2022, but real astronauts introduce variability that cannot be simulated. Breathing patterns, movement, heat generation, and daily activity all affect spacecraft systems. Artemis II allows engineers to observe how Orion behaves under true crewed conditions. The Space Launch System rocket also receives its first crewed evaluation. SLS is the most powerful rocket currently in operation, capable of producing more thrust at liftoff than any vehicle since Saturn V. Artemis II will test vibration environments, acoustic loads, and flight dynamics under crewed conditions. These factors directly impact astronaut safety and spacecraft longevity. Navigation in cislunar space is another major objective. Orion must continuously orient itself to maintain solar power generation, antenna alignment, and thermal balance. The spacecraft uses star trackers, inertial measurement units, and ground-based tracking networks to determine position and velocity. Artemis II demonstrates that modern navigation techniques can support crewed missions far from Earth with the precision required for future landings. Throughout the mission, astronauts will conduct operational tests, including manual piloting, system diagnostics, and emergency procedures. Cockpit interfaces, touchscreen displays, and control layouts will be evaluated for usability under real mission conditions. NASA needs to understand how crews interact with Orion over multiple days, including workload management, fatigue, and situational awareness. These human factors directly influence mission design for Artemis III and beyond. Artemis II is tightly linked to NASA's broader Artemis architecture. Artemis III aims to land astronauts near the Moon's south pole, an area of significant scientific interest due to permanently shadowed craters that contain water ice. This ice could potentially be processed into drinking water, breathable oxygen, and rocket propellant. Establishing sustained operations on the Moon would reduce reliance on Earth for resupply and create a stepping stone toward Mars. But none of that is possible without proving basic transportation first. Artemis II confirms that humans can safely reach lunar distance, operate in deep space, and return home. International partners play a central role. The European Space Agency provides Orion's service module, which supplies propulsion, power, thermal regulation, and life support consumables. Canada contributes robotic systems for future missions. Several additional nations participate in Artemis planning and infrastructure development. Artemis II demonstrates that this multinational system functions as intended. The mission also validates NASA's approach to incremental testing. During Apollo, Early missions verified individual systems before attempting lunar landings. Artemis follows the same model. Artemis I tested hardware without crew. Artemis II tests hardware with crew. Artemis III attempts surface operations. Each step builds on the previous one. Deep space missions carry inherent risk: launch failures, system malfunctions, radiation exposure, and high-energy re-entry, all present hazards. Artemis II is designed to identify weaknesses before astronauts are committed to more complex objectives, such as surface stays or extended habitation. The astronauts selected for Artemis II represent a cross-section of experience, including veterans of the Space Shuttle and International Space Station. Their feedback will directly influence spacecraft design refinements and operational procedures. One of Artemis II's less visible but most important outcomes will be data. Thousands of sensors throughout Orion will record temperatures, pressures, vibrations, radiation levels, and system performance. Engineers will analyze this information for months after the mission, identifying trends that may not be immediately obvious. This data feeds directly into safety margins for Artemis III and future missions. Beyond the Moon, Artemis II supports NASA's long-term goal of sending humans to Mars. Mars missions require spacecraft that can operate autonomously for years, manage radiation exposure, recycle resources, and support crews far beyond immediate rescue capability. The Moon provides a nearby proving ground where systems can be tested, refined, and validated. Artemis II is not about discovery in the traditional sense. It does not carry major scientific payloads or attempt surface exploration. Its purpose is infrastructure validation. Without Artemis II, every future crewed mission beyond Earth orbit would rely on assumptions rather than verified performance. The mission represents the rebuilding of deep space human capability after half a century focused on low Earth orbit. If successful, Artemis II confirms that modern spacecraft systems, life support technologies, and navigation methods are sufficient to support sustained exploration. If problems emerge, they will shape the next phase of engineering development. Either outcome provides essential information. Artemis II marks the point where exploration moves from concept to capability. It is the bridge between decades of orbital operations and the next era of human presence beyond Earth. In practical terms, Artemis II also tests something that rarely gets public attention: recovery operations. After re-entry, Orion will splash down in the Pacific Ocean. Navy recovery teams will secure the capsule, extract the crew, and transport the spacecraft for inspection. Every step of this process matters. Astronaut health monitoring, capsule integrity, heat shield condition, and avionics performance are all evaluated within hours of landing. These procedures are part of the mission. NASA needs to confirm that crews can be safely recovered after high-energy lunar returns, not just low Earth orbit flights. Another critical element is communications. During Artemis II, Orion will rely on NASA's Deep Space Network, a global system of large radio antennas located in California, Spain, and Australia. These stations provide continuous coverage as Earth rotates. The mission will test data transfer rates, command reliability, and voice communications over hundreds of thousands of kilometers. Deep space communication delays are small compared to Mars missions, but they are large enough to change how crews operate. Artemis II allows mission controllers to refine procedures for working with astronauts who cannot receive instant responses from Earth. Power management is also under evaluation. Orion uses solar arrays instead of fuel cells, which means power availability depends on orientation and distance from the Sun. Artemis II will measure how effectively the spacecraft balances power generation with life support demands, thermal control, and onboard systems. These results directly affect mission planning for longer flights. Crew health monitoring will extend beyond radiation exposure. NASA will track sleep cycles, fluid shifts in microgravity, muscle response, and overall physical condition. Even on a relatively short mission, these factors provide insight into how astronauts adapt when leaving Earth orbit. All of this feeds into future vehicle design and mission architecture. Artemis II is often described as a test flight, but in reality, it is a full operational rehearsal. It exercises launch systems, spacecraft performance, human factors, mission control coordination, and recovery logistics in one continuous sequence. This integrated approach is what distinguishes Artemis II from earlier uncrewed tests. It is the first time all elements of NASA's modern deep space system operate together with humans on board. The mission also carries symbolic weight. For a generation of engineers and scientists, Artemis II represents the return of human capability beyond Earth orbit. Many of the people working on this program were not yet born during Apollo. Artemis II validates decades of accumulated knowledge, new materials, modern computing, and advanced manufacturing. It marks the transition from rebuilding to moving forward. Once Artemis II is complete, NASA will have real-world data on how its spacecraft behaves in deep space, how crews perform under lunar mission conditions, and how ground systems respond to extended operations. That information determines schedules, safety margins, and design choices for Artemis III and later missions. This is why Artemis II matters.